So let's move now to talk about chromatography. So chromatography operates on the same principle as extraction. And when I'm talking about extraction, I mean the both type of extraction, the liquid-liquid extraction and the solid phase extraction. So in chromatography, we have two phases, a stationary phase and a mobile phase. And because I said it applies the same principles in both liquid-liquid extraction and solid phase extraction, that means that our stationary phase is not always a solid. The stationary phase can be either a solid or a liquid. But the liquid here, because it's stationary, it has to be a fixed or it has to be bound to be bonded to a stage to a solid material that is fixed in place. So we can either, as I said, as a stationary phase, you can have either have a liquid or a solid. And then we move on to the a mobile phase, and the mobile phase here doesn't have to be liquid all the time. It can also be a gas, which is called a carrier gas. So this gas does not interact, it just carries the substance along the column, as we will see in gas chromatography. So this is just an illustration of how chromatography works as an introduction. So now you have your solute, and solute here is your analyte. Your analyte starts off with being in a mixture, and you want to separate your mixture. So let's say that you have a mixture of two substances, A and B, and you have your column here, and this column is backed with the stationary phase. And as I said, the stationary phase can be either a solid or a liquid that is bonded to a solid material. And then you start off by putting mixture, including the analyte that you want to separate or you want to identify or want to get it in a pure form. And you start off with an initial band from both A and B. And then you start to add your mobile phase. And as you add your mobile phase, the two different solids, I'm sorry, the two different analyte or the all the different substance within your mixture will then distribute themselves between the stationary phase and the mobile phase differently, depending on their affinity for both phases. So by time, these two substances start to separate themselves and form separate bands. And if we have more affinity for the mobile phase and less affinity for the stationary phase, then it will be eluted first or come out first out of your column. And if you continue your elution, then you will end up by getting a also in a pure form or separated from B. So some definitions we need to be familiar with. So the fluid that we put inside our column is called the eluent. And the liquid that comes out of the column is called eluate. So you have your eluent and you have your eluate. As we said, the partitioning will take place will take place depending on the affinity for both phases, and at the end you end up with two separate components, or you separate the different components using your chromatographic method. So, what are the different principles for the operation of the chromatography? So, what type of affinity are we talking about? And based on this affinity, how can we separate the different component in any sample? So, there are um, five main principles for this separation. So, the first one is adsorption. And in case of adsorption, we have a solid phase, stationary phase. The stationary phase is a solid, and the mobile phase here could be a liquid or could be a gas mobile phase. So you have a solid and then a liquid or a gas as a mobile phase. and then your analytes will be absorbed on the surface of the stationary phase. And as the mobile phase runs along the column, the different component will be separated based on their affinity to the mobile phase and their how strong they are adsorbed on the stationary phase. So some substance will be more adsorbed than the others. So this is the first one, adsorption. Of course, more strongly adsorbed substance will stay longer on the column and will be eluted later. The second one is partition. So partition uses the same principle as the liquid-liquid extraction. So in this case, the stationary phase will be a liquid, and this liquid is bonded to a solid surface. And then you have your mobile phase, which is liquid, could be a liquid or gas as well, and the solute will equilibrate itself between the stationary phase and the mobile phase. So you would think that for partition, it's mostly going to be liquid mobile phase, because then your substance will be distributed between these two mobile phases. So it's more like the liquid-liquid extraction. The third type is the ion exchange. And as the name implies, ion exchange means that we have some ions, either cations or anions, on the surface of the stationary phase. So your stationary phase can have some anions or some cations. And normally you would think that if your solute has the opposite charge, it will have some electrostatic interaction with that charged ions on the surface of the stationary phase. So if you have an ionic stationary phase, then if you have any cations in your mixture, then it will be retained on the stationary phase, and anything else will be eluted quickly, and vice versa. So if you have a cationic stationary phase, then any anions in the mixture will be retained and the other will be eluted quickly. And then we have molecular exclusion or size exclusion. Again, the name explains itself. So that means that we have a solid stationary phase that has some pores of a certain size. And that certain size allow the retention of certain size molecules. So larger molecules will be eluted quickly because they cannot be retained in the pores. While the smaller ones can be retained. So this is another. This is when of course, we have to use the proper type depending on the type of sample we have. So depending on what type of samples you have, you will use the proper type of the stationary phase. So this is usually we can use here liquid or gas as a mobile phase, because it mostly depends on retention of your molecules in the pores. So gases can easily push away the larger molecules. So we can use either liquid or gas as our mobile phase. And then the last one and the most selective one is the affinity. And affinity means that you have specific, um, it depends on a specific interaction between the analyte and a second molecule that is covalently bonded to the surface of the stationary phase or on the surface of a solid. Example of that is the antigen antibody interaction. So you can have an antibody that is specific for a certain antigen, and then this antibody is fixed on the surface of the on a solid on the stationary phase, and then your sample then will have, if it has the antigen will just interact with that specifically with that antibody, and this is the only thing that will be retained. Anything else will be eluted quickly. So these are the 5 different main principles of chromatography and the different types of columns or different types of stationary phase that we can use. Of course, again, as I said, it will always depend on the nature of your component or of your sample. So a certain principle or a certain type of chromatography can be suitable for certain sample, but not for another. So you have to be careful when you choose what type of columns do I need to use. Um, uh, One of the things that we will always encounter in chromatography is the flow rate. So if you have read any paper that people are doing some type of chromatography in it, like using HPLC or gas chromatography, we will always find the term flow rate. So what does flow rate mean? So flow rate from the name means um, it means how much. So there are two types of flow rate. So there is something called volume flow rate, and there is something called the linear flow rate. So volume flow rate exactly tells you how many millimeters of the solvent per minute will travel through your column. So you need to know exactly how many milliliters of your solvent will travel through your column per minute. So it's about volume. And the linear flow rate then will tell us how many centimeters are traveled in 1 minute by the solvent. In order to find or calculate the volume flow rate, we need first to know how much solvent are there in the column. And how much solvent is in the column will depend on the volume of the column itself and the percentage of the solvent or of the eluent inside the column. So if we consider that we have a column has an inner diameter of 0.6 centimeter, so the radius will be 0.3 centimeter, and the mobile phase occupies 20% of the column volume because the column will contain the stationary phase. So the mobile phase will only have a certain, will occupy only a certain volume of that column. So each centimeter of the column length will have a volume equals to the pi r squared times the length of the column. The length here is 1 centimeter because we are talking about how much what is the volume of 1 centimeter. So now we said that this specific column we are talking about has a radius of 0.3 centimeters. So when you calculate the volume, it's 0.283 mil. So this is the volume of your 1 centimeter of the column. 20% of that volume is your mobile phase. So your mobile phase is 0.0565 mil. Now the volume flow rate is 0.3 mil per minute, for example. So that means that 0.3 mil of our solvent will travel through the column per every minute. Now we want to calculate the linear flow rate. So the linear flow rate will tell us how many centimeters are traveled in 1 minute by the solvent. So the linear flow rate corresponding to the volume flow rate of 0.3 mil per minute is going to be calculated as the volume flow rate, which is 0.3 mil per minute divided by the volume that is occupied per 1 centimeter, which is 0.0565 mil per centimeter. So when you do your calculation, you will find that it's actually the linear flow rate is 5.3 centimeter per minute. So you to calculate the linear flow rate, then you divide the volume flow rate, which is 0.3 mil in this specific example, by the volume that is occupied, the volume of the mobile phase that can be held in 1 centimeter of your column. So that will give you the linear flow rate. Few definitions before we move on to talk about the efficiency of our columns or the efficiency of separation. So chromatogram, we all know what is chromatogram. So a chromatogram is the graph that shows the detector response as a function of elution time. Because in chromatography, elution times means everything for us. So we will see how many components we have based on their elution time. So the elution time is very important. So the graph or that shows us the detector response versus the elution time, this is called chromatogram. And then there is the retention time. So retention time is another thing that is very important. And retention time for each component is the time between the injection of your sample until this component is out from your column and as it reaches the detector. So this time that elapsed is called the retention time. There's something also called the retention volume, and from the name, it will probably be very clear that retention volume is the volume of the mobile phase that you had to use from the minute or from the second, or from the moment you injected your sample until your component is eluted. There is also some solvent or unretained solutes. They never retained on the mobile on the stationary phase. They are eluted straight away, like methanol, for example. So this is a solvent and it's eluted quickly because it's never retained. So this is called a dead time. This is called dead time. So the dead time, which is TM, is basically the time required for this unretained solute to be eluted from the column. So how much or how long did it take until it's completely eluted from the column? So now we come to what is called adjusted retention time. So adjusted retention time is basically the difference between the retention time and the dead time. So we can also calculate the time for our sample or for our particular analyte to come out of the column, but from the second or from the minute or after the elution of the unretained solute. So this is called the adjusted retention time.